Buddy, Professor Hartman here. I'm going to work through a couple of questions from Chapter 8 here. This is the topic on rotation. It's an interesting topic. Basically, it's all the same old concepts we've been dealing with, but now it's applied to the rotational world. So let's start. This is Chapter 8, number 18. You're told that a centrifuge accelerates uniformly from rest to 15,000 RPM, and it happens in 240 seconds. This is a pretty straightforward question. It's basic kinematics just applied to rotations. We're told, and since we're asked for revolutions, we can stay in RPM, because that is revolutions per minute. So basically, our initial angular speed is 0, right? Because we're told that we start, let's work in revolutions per second, okay? So we know that basically we start at 0 revolutions per second because they say it accelerates from rest. Our omega final, we need to deal with that because right now it's in revolutions per minute. So 1500, right, revolutions in 1 minute. And we want, let's say we want to work in RPS, right, revolutions per second, just because our time is given in seconds. You could choose to work in minutes. That would be 4 minutes. Same thing. That might even be easier, but we're already doing this. So, okay. Well, obviously in 1 minute, right, there are 60 seconds, right? So then that'll, the minutes will cancel out, and we'll have revolutions per second, right? So it's basically going to be 1500 divided by 60. So let's see what that gives us. 1500 divided by 60 is 25, right? So we have 25 revolutions per second. 25, revs per second. Okay, great. We can also now get alpha, right, the angular acceleration, because alpha, right, is basically the change in omega over the change in time, right, and it's going to be angular acceleration. So we know that our change in omega is 25, right, because it starts from 0, goes to 25 revs per second over 240 seconds. So if I do 25 divided by 240, we'll get 0.10 revs per second squared. Okay, so now we have our initial angular velocity, we have our final angular velocity, and we have our angular acceleration, so we can get delta theta. We can use the time-independent kinematic equation, which says this, right, that omega final squared equals omega initial squared plus 2 alpha times the change in the angular displacement. This is, of course, 0 because we started, from rest, so that's gone. So we have this relationship here where it's just omega final squared equals, and these are vectors. Well, this one's really not. Let me not do that. If we wanted to get really strict about it, like this is a vector and this is something called a dot product and this is another vector, and then when you square this, it's actually a scalar, but it's really not that important for what we're doing here. So I'm just going to write it like this, even though it's a little sloppy, but yeah. Okay, and we want delta theta, right? That's what we're looking for. So if I go ahead and just divide both sides by 2 alpha, we can find that the angular displacement, right, which is again what we're looking for, is omega final squared over 2 alpha. And we can plug this stuff in. We know omega final squared is 25 revs per second. So I'm going to call it RPS, revolutions per second, just for simplicity, over that. Times 2, and then what we have here is revolutions per second squared, so this is going to be 0.1 revs per second squared, like that. And so we'll just go ahead and plug these in, basically. It's going to be 25 squared divided by 0.2. So 3125 revolutions. So it's 3,125, and we're in revolutions, so revs, revolutions. So that's the answer to that one. If you wanted to go into radians, you would just divide by 2 pi. So that's that one. Pretty straightforward. Number 34 is a little more involved. Let me make this a little bigger. Here. There we go. There we go. Okay, so you're told that a grinding wheel is a uniform cylinder with a radius of this and a mass of this, and you want to calculate its moment of inertia about its center. Well, for this, pretty easy. The moment of inertia, you can derive these things. It requires a little bit of calculus, but in general, you're just going to be given a list of these things. And for the solid disk, right, basically, essentially we're envisioning our disk as sort of like, or a cylinder is sort of like something like this, and like here's the axis, right? And this thing is like rotating like that, and here's the radius, like that kind of thing. The cylinder, in general, right, the moment of inertia, which is given by I, which is effectively a measure of rotational mass. It's really just a measure of the resistance to any kind of acceleration. In this case, angular acceleration. For the disk, for the solid disk, which is what a uniform cylinder is approximated as, it's given by this. You would just look this up in your book. This is in that table in the textbook of moments of inertia. And we have all the things. We have the mass, we have the radius, so it's just going to be a half. The mass of this thing is 0.380 kilograms, so 380 kilograms. The radius is 8.5 centimeters. We got to be in meters, so 0.85 meters squared. And now we just plug it in. So 0.085 squared times 0.380 divided by 2, and we get 1.37. So approximately 1.4, let's say. 1.4 times 10 to the negative 3, and the units are kilogram meters squared. That's the units of the moment of inertia. So basically this is like the rotational version of mass. Just like a mass resists a force, a moment of inertia resists a torque. Part B asks about the torque. So for Part B, they want the torque, and you're given some information here. You're told that it starts at rest, so omega initial is 0. And here we have to be in radians per second. When you're dealing with torques, it means we're going to have to deal with newtons. You definitely need to be in standard SI units, which would be radians here. So we're going to have to convert omega final. We're given omega final, and we're told that this is 1750 RPM, right? So 1750 revolutions, right, in 1 minute, times, we want to be in radians per second. So there are 2 pi radians in 1 revolution. You go around the circle once is 2 pi. And then obviously there are, in 1 minute, we have 60 seconds. Right? And this will give us the right units because we'll end up with radians per second, because these minutes will cancel these minutes and these revs will cancel these revs. So we have radians per second. So we got to do 1750 times 2 pi. And then we're going to divide that number by 60. And we're going to get 183.3 radians per second. So 183.3. Okay. The time is 55 seconds, which means that we can get alpha, right? Because alpha is the change in omega, right, over the change in t. The change in omega is 183.3 radians per second, because it goes from 0, divided by 55 seconds. So here we'll go ahead and we'll get the get that number. That's about 3.33 radians per second squared. So that's our angular acceleration. So now we can get the torque, right? So the second law, right, Newton's second law, right, in linear form, it's F equals ma, right? But in rotational form, we're dealing with torques. It's torque, tau, which is the Greek letter, basically it's a T, but whatever they call it, tau in Greek, equals I alpha, right? This is Newton's second law in rotational form. We have I, right? We solved for it in part A, and we found that it was 1.4 times 10 to the negative 3. So 1.4 times 10 to the negative 3 kilogram meters squared. And then alpha is this 3.33 radians per second squared. And we plug those in, and we're going to get our net torque. So let's check that out. So 1.4 times 10 to the negative 3 times 3.33. The net torque is 4.67 times 10 to the negative 3. So 4.67 times 10 to the negative 3. And the units for torque are Newton meters, right? If anyone is familiar, works with cars or anything like that, or not even just cars, but just, is sort of handy with tools, you'll be familiar with a torque wrench. And a torque wrench is measured in foot-pounds. It's a force times a distance. But here we do Newton meters to stay in standard SI units. Okay. But That was B. Oh, I left out the frictional torque. Oops. Okay. Well, I didn't include the friction. I just pretended there was no frictional torque at all. But if we had the frictional torque, let's we don't need to do that. I'll do another problem with the frictional torque later. Let's just pretend there was no frictional torque there. Let me just do this. If I were to include the frictional torque, right, it would be the torque that I just solved for. Maybe call this torque applied, right? So it would be our applied torque minus our frictional torque equals I alpha. And then the frictional torque, I'd have to figure this out with the information they give you. But basically the applied torque, the one that we're actually looking for, would end up being I alpha plus the frictional torque, where we'd have to calculate this frictional torque. And the way we would calculate it basically is the same way we just did, right? We'd basically just calculate, put this in radians per second, right? Because this would be basically delta omega. That divided by that. And then, so that would be the deal. Okay. Oh, I see what I did. I really screwed this up because this 55 seconds is for the frictional torque. So whatever. Sorry about that. Let's just pretend. Let's go ahead here and pretend that this never happened. And I'll show you how we fix this in our modern society here. And this time is really 55 seconds. So there you go. So now I didn't make a mistake. But I'll do it. I promise to do another problem where I actually do a frictional torque. That's not what we want here. Okay, so I thought I had another problem, but I guess I did not. No, I didn't want to do that one. Didn't want to do that one. Okay, yeah, I'll post some more problems. Ones where I don't make a mistake with the frictional torque like that. Anyway, I hope this was useful despite my slight error there.